Hi guys, Dr. Justin Southey here, going through semester test 2, and I'm looking at question 14, where you're asked to prove that the hyperbolic tan of the log of x, the natural logarithm of x, is equal to x squared minus 1 all over x squared plus 2. Now remember, when you're asked to prove something, it is very, very important that you use the correct notation and that each step follows from the previous and is easily justifiable. What a lot of you ended up doing was to write some sometimes sensible arguments that led from hyperbolic tan of log of x to something. Then you get a little bit confused and you just write equals the right hand side. We are watching. So let's see how we do this properly. Hyperbolic tan of the log of x. First we need to know the definition of hyperbolic tan. Well, you know that's hyperbolic sine over hyperbolic cos. So we've got hyperbolic tan of the natural logarithm of x is equal to hyperbolic sine of log of x divided by hyperbolic cos of the log of x. Now you need to know the definition of hyperbolic sine. Well, remember, hyperbolic sine of x is simply e to the x minus e to the minus x all over 2. Here, of course, we don't have hyperbolic sine of x. We've got hyperbolic sine of log of x. So wherever we had x in our original definition, we now need to substitute it with log of x. So this is equal to definition of hyperbolic sine, e to the whatever's in here, so that's log of x, minus e to the minus whatever's in here, so that's log of x, all over 2. That now is hyperbolic sine, and we're dividing that by the hyperbolic cos. I'm going to write it as the division sign just because we're getting a whole lot of fractions and it's getting a bit cumbersome. Hyperbolic cos is e to the, in this case, log of x plus e to the minus, in this case, log of x. And all of that is divided by 2. Let's do a little bit of simplification. Now, this one's easy. You know what's going there. I'm going to leave it as it is for now until we've simplified the next little bit. E to the log of x minus, now here we've got e to the minus log of x. In this case, log and e are inverse functions. So if I take the log of something, the natural log of something, and then I raise e to the power of the answer, well, I just get back to what I started with. So this thing just simplifies down to x, but we can't do that here because here we've got e to the minus log of x. So we need to try and get this minus away from in front of the log, and we've got a nice log law to deal with that. So this is that bit there is e to the log of x to the power of minus 1. Remember, this is a minus 1 in the front, so you can take it inside the log and use it as a power. And that's over 2. And now I'm going to flip this fraction over. Dividing by a fraction, we can multiply by the reciprocal. So that's times 2 over e to the log x. I'm going to leave as log x. For those of you who are wondering why I'm saying log and not a natural logarithm, remember that e is such a common base that in fact in most textbooks when they refer to log, they're actually referring to the natural logarithm. So here we've got e to the log of x, or e to the natural log of x, plus e to the, and we're going to use the same trick here. We're going to take that minus 1 into the log as an exponent. So we have the log of minus 1. Now we've got some nice things that cancel down quite nicely. That 2 and that 2 over there. And we're left with, now, e to the natural logarithm of x. As we said just now, if I take the log of x and then I raise e to the power of it, I'm simply left with x. Here I've got the same thing. I take x to the minus 1, I take the log of that, then I raise e to the power of the answer. I get back to what I started with, their inverse function. So that's x to the minus 1. That's in the numerator. And in the denominator, I'm left with x, because e to the log of x is simply x, plus e to the log of x to the minus 1 is simply x to the minus 1. And we're getting closer. We're getting something that's looking more and more like the right-hand side. The last step is simply to multiply through by x over x. So we multiply the top by x, and we multiply the bottom by x, and we are left with x squared. x times x to the minus 1, well, same basis, so you can add the exponents. Plus 1 minus 1 is equal to 0. X to the 0 is simply equal to 1. And same on the bottom. Oh, I've left out a plus over here. On the bottom, we're left with x squared plus x times x to the minus 1. Well, that's also just x in the numerator divided by x in the denominator, again, is equal to 1. And here you've got a series of steps. 1, 2, 3, 4, 5, 6. Each one follows logically from the previous one, and it proves that the left-hand side is equal to the right-hand side.